Check it out now, y'all.
nanoHUB-U online instruction.
Okay, today we're going to talk about the homework associated to week 5, the last week. The first question is, using the reaction zone model, at what porosity epsilon does the classic porous electrode of thickness H sub C maximizes the delivered energy? Okay, so what we learned, the main two equations that we learned this week was that the voltage of the battery is related to the current, in this case I, the current density, by subtracting the polarization losses from the equilibrium potential U, where H sub S is the thickness of the separator, kappa S is basically the conductivity associated to the separator. We're assuming that the losses along the separator are not any different than the losses if we had only electrolyte, although those numbers could change in general, minus the losses as a result of the reaction zone. And because the conceptual picture here that we are describing corresponds to having one electrode whose separator has a thickness H sub S, and here inside there's a section that has not been used. Basically that whole section over here is the active material that is ready to be used, and to that we're subtracting these losses and the loss associated to the material that we have already utilized that has, with respect to where the thickness of the electrode is, that corresponds to X of R, right? That distance from the edge of the electrode to where we have actually penetrated in the system, okay? And, well, the whole electrode has a thickness H sub C, right? Which is basically what the statement of the problem says, okay? Now, the idea of the second term is that as we further utilize the electrode, this loss, this polarization loss, increases until we reach the utilize in its entirety the system, right? Which typically occurs when T equals TD, which we call TD in this case the discharge time. Okay, that's in general, okay? And in this case, equation number 2 corresponds to the balance of material, basically how much of the charge that we have injected here at a current density I, okay, how much of that has been spent on the reaction zone. Okay, so if we have a certain capacity that the material has that we basically account for through this entire term, okay, this basically accounts for the porous active material. If we do that, that corresponds basically, the injected charge corresponds to the utilized charge, basically the two conceptual parts that we're using in this model. And if you do that, well, the energy of the system conceptually corresponds to the integral from 0, but that is the instant that the battery starts to be discharged, to T equals TD, the discharge time, okay, of the voltage times the current, right? This gives us the power of the battery integrated over the entire time, right, from 0 until it discharges. Well, that will require us to basically take equation 1 and substitute it in there, okay, and well, if we integrate that, we basically get U I times TD minus HS I squared over kappa S TD, right? These two terms don't have any time dependence, and that's why we can just multiply those terms like that, right? Minus, in this case, this current multiplies that current squared, so we get a current cube. Okay, we have the entire denominator, kappa S epsilon to the 3/2, 1 minus epsilon Q. And in this case, this one indeed has a time dependence there, which we're integrating, so we end up getting a T squared divided by 2, which is basically the term that accounts for all the losses in the system. And this goes from 0 to TD, so this T basically ends up being that number. Okay, what is actually TD in this case? TD corresponds to the instant at which the electrode has been utilized. Mathematically, this corresponds to the case where we go into this equation and substitute T by TD, so we can say that 1 minus epsilon times Q times X of R, but in this case X of R corresponds to H sub C because X of R has moved from this edge to the other edge, and that equals to I times TD. So you can see how I can take this entire expression and directly substitute it in here and get a linear and quadratic contribution to the thickness of the electrode H sub C. So you can see how the thicker my electrode is, the more energy I'm storing, but the bigger the polarization losses, and in this case linearly as you make it thicker, and the greater the reaction losses. In this case they go as a square. Okay, now how do I calculate those extrema? In this case, in the case of polarization, notice that the term that dominates all the kinetics, okay, is that term over there. Okay, so you can see how for epsilon equals 0, this term basically blows up to infinity, and for epsilon equals 1, it also blows up. So if there is an optimal value, it should be between 0 and 1. So basically this term over here is controlling the kinetics. So I'm going to define that function f of epsilon as epsilon to the 3/2 times 1 minus epsilon. And, well, it's very straightforward here to simply say, well, if there's an optimum value, it should be between those two. So I'm just going to do this. Okay, basically there's some minus over there. Okay, from taking the derivative of that product, that's equal 0 to 0, and well, I can get rid of 1 epsilon to the 1/2 and say 3/2 times 1 minus epsilon minus, in this case, epsilon equals 0. Okay, and if I collect terms, I get that 3/2 minus 3/2 epsilon minus epsilon equals 0. So I can take here at 2/2. So that basically gives me that 3/2 minus 5/2 of epsilon equals 0, which means then that the critical value of epsilon corresponds to 3/5. Okay, which corresponds in this case to answer B. Okay, and this one is the optimal porosity. Okay, where basically this function goes through an extremum value. Okay, basically it goes up and then comes down, which means that this one blows to infinity, comes down, and then comes back up, right? So that corresponds to when this term actually reaches a minimum. The way I did it really is just one possible way. You could have just simply, and I'm just going to do it in this corner over here, you could have simply said dE d epsilon equals 0, and you would have found the exact same thing, except it would have been a little bit messy because the 1 over that term would complicate things, but you would have gotten the exact same number. Okay, so that's for that question. Question number 2, using the reaction zone model, at what electrode thickness does the classic porous electrode maximize the delivered energy? The mechanics is the same, except that now I actually have to substitute TD, okay, and substitute H sub C in there. And if you do that, you will end up with a quadratic. Okay, you solve for that quadratic, and the answer in this case corresponds to answer E. Okay, which I'm not going to write, but basically what it says is that the thicker you make your separator, the bigger your losses, and the optimal thickness depends on the current that you're using for your application. Okay, and well, that concludes the main part of the main analytical part of that model. Okay, question number 3. Okay, it says, which of the following is not a valid assumption in the reaction zone model, which is basically what we discussed. There are 5 possibilities. One of them is that all current density is converted into reactive charge. Notice that that is indeed a valid assumption, because that's basically what we're saying there with equation 2. We're saying that whatever charge we inject into the system is actually used to move the reaction zone, okay? Which then, that is not the answer we're looking for. Ohmic limitations are included. In this case, for the reaction zone model, that's actually the only thing that we're indeed including in the model. Basically, this one corresponds to the polarization loss from the separator, and this one corresponds to the polarization loss from the reaction itself. So those two are included in this description, so it cannot be answer B. Okay, answer C says diffusion limitations are included. If you remember, when we were going over the description of this model, we were explicitly assuming that diffusion limitations are not included in this description. We do expect that as we increase the current density in this model, more material would accumulate internally on the surface of each particle, making then this model useless for the case where diffusion limitations in the particles are relevant. Okay, so therefore the right answer for question 3 is C. Okay, the other 2 answers that are left is porosity is uniformly distributed throughout the electrode. Yes, that is indeed an assumption. And in fact, we assume that the porosity, as we go along, the thickness of the electrode is always going to be the same, regardless if the material is reacted or unreacted. In a real battery, you expect that those pores to open up and close depending on how much charge you're putting in the system. In fact, depending on what specific chemistry you're looking at, some particles can expand. Say if it were graphite, for example, it will expand up around 12%. And if it's, say for example, silicon, it could expand all the way to 500%. So in theory, you can actually close those pores simply by intercalating, which is something that this model doesn't include. So a valid assumption is that porosity is uniformly distributed. So that is also, of course, not an answer. Finally, the equilibrium potential is state of charge independent. That is true. In fact, you can see that the equilibrium potential U is always assumed to be state of charge independent. In general, we expect that U actually depends on what the average state of charge is. In fact, you could think of a more complicated model, more sophisticated model where U is actually could be a function of X of R, basically depending on what the average state of charge is. If I'm fully charged or fully discharged, how that boundary is moving will impact on what the shape of that potential will be. And you could think of that as a much more sophisticated version of that the basic formulation doesn't have. Okay, this model again only accounts for the polarization losses, does not include for the diffusion losses. And because of that, during that week, we also discussed the contributions from diffusion using porous electrode theory, which that is the last question of the homework, where it says which of the following is not a valid assumption of porous electrode theory. Possible answer A says that particles of the active material are perfectly spherical, and even this model, both models assume that the particle size are perfectly spherical and perfectly uniformly distributed. In this case, we assume, in both cases, that the particles are always perfectly spherical, okay, and that there's no orientation dependence. So we only care about the radial distribution of the reactant, or lithium for that matter, okay. Okay, and because the particles are spherical, that means that we're assuming that always the tortuosity goes as 1 over epsilon to the 1/2, which both models, the reaction zone model and porous electrode theory, both assume this description, okay? Maybe you can, in theory, go back and replace that with a much more generalized description where tau equals A over epsilon to the B. You could do that, although what we discussed in class, we do not include those effects, but that's an obvious derivation that you can do, an additional construction. So that obviously is not the answer. ohmic limitations are included. Historically, actually, the reaction zone model was developed after the classic porous electrode theory was derived. So this model, both models include the ohmic losses. So that is obviously not the answer either. Answer C, phase transformations inside the particles of active material are included. That is something that the classic porous electrode theory doesn't have. We assume that the radial distribution of that reactant as it goes, it's driven by diffusion only. Okay, so in a real battery, you could have two or more phases competing with each other for lithium. So because this model, the classic model, does not include that, then that is an assumption that is not included. So therefore, phase transformations are not included in this description. Possible answer D is that diffusion limitations are included, and yes, we do include them. They are included to the point where we can account for how much lithium is included, how much lithium is effectively, how fast the lithium is actually distributed inside the particles, and it also says how the lithium is distributed as it goes through the electrolyte or whatever reaction you're looking at. And finally, transfer properties are uniformly distributed. That's one of the main assumptions of the Newman model, where basically you're saying that this porosity is not position dependent. There has been extensions in the literature where people have started to do that or have done that, but the classic model that we discussed this week does not include those effects at all. So for all practical purposes, you can think that the porosity is uniformly distributed and you don't have those porosity inhomogeneities that would change the tortuosity of the system as well, as we have discussed as well. So for question 4, the right answer was C, phase transformations inside the particles of active material are not included. Thank you.